Welcome to all. I am going to present about the air conditioning problem, as well as going to discuss about the environmental factor regarding the air conditioning. This first problem is going to calculate the mass of dry air entering is 1 kg per second. The air vapor mixture leaves the air conditioning unit at 1 bar. 18 degrees Celsius, 85% relative humidity. The moisture condensed leaves at 18 degrees Celsius. Determine the heat transfer rate for the process. How much heat transfer rate will be in this process? That is the question. An air-water vapor mixture enters an air conditioning unit at a pressure of 1 bar, 38 degrees Celsius dry bulb temperature and relative humidity of 75%. So we know that dry bulb temperature as well as the rehumidification value and then PV value calculated from the rehumidification percentage multiply with PV and W1 value also obtained from the psychometric chart. Heat transfer rate also obtained from the following equation. Q is equal to W2 Hg2 minus W1 Hg1 plus Cp multiply with dry bulb temperature 2 minus dry bulb temperature 1 plus W1 minus W2 multiply with HF2. The saturated temperature is 3 degree Celsius is required to be supplied to a room where the temperature must be held at 22 degrees Celsius with a relative humidity of 55%. The air is heated and then water at 10 degrees Celsius is sprayed to given the required humidity. Determine the mass of spray water required per meter cube of air at room condition. Mass of spray water required Wg is equal to 0.00904 kg per kilogram of dry air. W1 value is equal to 0.0047 kg per kilogram of dry air. VA3 is equal to RA multiplied with T3 divided by PA3, and the small diagram will represent the following questions and requirements. The saturated air at 30 degrees Celsius will be at section 1, and then the air flow into the heater and then enter into the spray nozzle through section 2. After reached the air into the spraying section, again the air will enter into the room with 22 degrees Celsius of 55% rehumidification condition. The spray water also calculated from the moisture per meter cube value. Temperature to which the air must be heated, dry bulb temperature 2, where H2 plus W3 minus W2 multiply with H4 is equal to H3 formula utilized to calculate this, and then the Cp multiply with the dry bulb temperature plus W2H vapor 2 will be added with W3 minus W2 multiply with H2 is equal to Cp dry bulb temperature 3 plus W3H vapor 3. This formula is also considered in the following equation, where the Cp into dry bulb temperature 3 minus dry bulb temperature 2 plus W3 enthalpy vapor W3 minus W2 H vapor 2 minus W3 minus W2 multiplied with H4 is equal to 0. Through that we can calculate the dry bulb temperature too. And from this problem we are going to calculate the amount of cooling water makeup required per second. The final temperature of the water is also calculated. Assume that the pressure remains constant throughout the tower at 1.013 bar. A small size cooling tower is designed to cool 5.5 liter of water per second. The inlet temperature of which is 44 degrees Celsius. The motor driven fan induces 9 meter cube per second of air through the tower and the power absorbed is 4.75 kilowatt. The air entering the tower is at 18 degrees Celsius and has a relative humidity of 60%. The air leaving the tower can be assumed to be saturated and its temperature is 26 degrees Celsius. In the schematic diagram is clearly showing that air entering and air exit as well as the cooling water entering and exit where the hot water supply into the chamber and then the fan is circulating the air from suck out the air from inside to outside in order to the sprayed water converted into cooling water which is outlet of the bottom of the section where the PV value obtained from the formula. PV value is equal to by multiply with PV by mass flow rate of air is equal to 10.78 kilogram second and mass flow rate of V1 mass flow rate of V2 also obtained from the values. Makeup water required also calculated and then Wi mass flow rate of water W1 H W2 plus mass flow rate at air at 1 HA1 plus mass flow rate V1 HV2 is equal to mass flow rate of air at 2 HA2 plus mass flow rate of V2 HV2 plus mass flow rate of W2 multiply with HW2. Finally, we can find out the final temperature of the water. And also we discuss about the desirable thermodynamic properties and environmental safety aspect of alternative refrigerants. The desirable thermodynamics properties. The saturated pressure of the refrigerant at a desired low temperature should be above or equal to the atmospheric pressure in order to avoid leakage in the evaporator. The pressure at the condenser must not be excessively high for the same reasons. The latent heat of evaporation at the low temperature should be as high as possible to give a reasonable low mass flow rate of refrigerant for a given refrigerant capacity. The size of compressor depends on the specific volume of the refrigerant at evaporator pressure. Thus, the specific volume of the refrigerant at the compressor section should not be high in order to avoid large compressor for the required mass flow rate. The refrigerant should be chemically stable and should not react with lubricant used in reciprocating compressor and should be miscible with oil. Should not be non-flammable and non-explosive. It should be non-toxic. If toxic, gentle a limit that is below the acceptable value. It should have low specific heat of liquid for better heat transfer in condenser. The refrigerant should give high value of COP with the low power input per ton of refrigeration. The refrigerant should have good thermal conductivity for better heat transfer in the condenser and evaporator. The refrigerant must have freezing point temperature well below the lowest temperature in the cycle. The chemical stability, non-corrosiveness, low cost and overall eco-friendliness and environmental safety aspects of alternative refrigerants. The chlorine refrigerants react with the ozone layer and try to destroy the ozone layer in the upper atmosphere by continuous chain reaction. The refrigerants that are friendly to the ozone layer in atmospheric that protect the earth from the harmful ultraviolet rays are called eco-friendly refrigerant. For example, R134A is a chlorine-free refrigerant since it is an eco-friendly refrigerant. Hydrocarbons HCS and hydrofluorocarbon groups provide an alternative to chlorinate refrigerant. They contain no chlorine atom and therefore it has zero ozone depletion potential. Two common refrigerant Freon 11 and Freon 12 are highly chlorinated and we are very harmful for ozone depletion. Freon 11 is replaced by HCFC 123 which has 98% less ozone depletion potential. Freon 12 is replaced by R134A with 0 ODP. The viable solution includes halocarbons refrigerants for CFC 12 R12 used in automobile air conditioning and household refrigerator, HFC 134A or 134A is permanent substitute OTP is equal to 0. For CFC is 11 or 11 used in centrifugal compressor and interior substitute is HCFC 123 until this group is phased out. HCFC 22 or 22 used in window and commercial air conditioning and refrigeration. Possible substitute is HFC mixer R407C and R110A.